Our first speaker here is Michael Good. So, Michael, if you can start screen sharing for us.
Thank you, Rick. Thank you for having me, and thank you for the invitation. And I also appreciate your efforts to run such a nice circuit. So let me tell you that my talk. I'm super excited to tell you that about classical acceleration temperature, this CAT. I'm based in Astana, Kazakhstan. Right now, I'm in the U.S., but a lot of this work is done with some of my very good colleagues. Morgan is in the audience right now, Dr. Lynch, and we know a lot of connections between temperature and acceleration currently in physics. Probably the famous one through the equivalence principle is that of Hawking radiation for the Schwarzschild black hole, where G is the surface gravity of the black hole. And you can see that using SI units, that H bar here kind of signals the fact that Hawking used quantized fields. C is the addition of special relativity, and Boltzmann constant signifies that this is thermodynamics. Now, there is a flying moving mirror model, which has been well known since the 1970s to also be an analog for black hole evaporation. And it has a temperature too, where this variable kappa represents a scale, an acceleration scale that characterizes the trajectory, the equation of motion of the moving mirror itself. It also uses quantum fields and is thermodynamic and a relativistic effect. And then there is the infamous Davies-Fulling-Unruh effect, that of a uniformly accelerated observer in Minkowski spacetime who finds himself immersed in a thermal bath. So alpha here, you can see, is the uniform acceleration. So several different connections between acceleration or surface gravity and temperature. But the effect that I'd like to tell you about today is one that is actually classical. So it stands out a little bit due to that reason. And you can see it is the effect here is the temperature of an electron, or if you will, more precisely, the temperature of the photons emitted by an accelerated electron. The temperature here is proportional to the electric charge squared and kappa. And now kappa has a particular meaning in this context, where it is related very closely to the flying mirror, more so than the uniform acceleration of the thermal bath, and more so than the gravitational, surface gravity of the Schwarzschild black hole. So this kappa here, I'll tell you a little bit more about it, but suffice to say, it actually corresponds to the one single dimensional acceleration scale, the parameter of the system, and we'll see it a little bit more clearly here in the trajectory. So this is not a uniformly accelerated trajectory like in the Unruh effect or the thermal bath of the uniformly accelerated Davies-Fulling-Unruh effect. This is a dynamic trajectory. It has time dependence. And a very simple way to express this trajectory is the inverse velocity here, where time is the coordinate time, r is a coordinate distance that's like a radius. It starts from 0 and goes to r equals infinity. C is the speed of light. S is the final speed of the electron. So it stays time-like in this Penrose diagram. You can see it's always below the speed of light. And kappa is the dimensional acceleration scale. So it doesn't really have any meaning besides a parameter that characterizes the particular trajectory. So this is a trajectory that I'd like to just suggest to you as an ansatz. It's what I'm going to assume, and I don't want to justify it. I don't want to have to motivate it. I'm just going to say, please accept this trajectory, and let's see what happens if an electron were to move along this trajectory. And I think that you'll be excited to see what the result is. So to give you a little bit more familiarity with what the dynamics are like, it starts off at zero velocity. So it starts off at rest. So an electron moving along this trajectory would be completely still in the far past. But then around time equals 0, it shoots up with its velocity and goes to its final speed, s. This is pretty much a Heaviside step function description for the velocity, if kappa is large enough, or if the speed is fast enough. So the acceleration, the proper acceleration here is always positive. So it's always accelerated in the direction of travel. It never has deceleration in the opposite direction. It actually just gets less positive in the future. So it has some maximum, and then it falls down to zero in the far past and far future. So it's completely asymptotically inertial, a very physically realistic type of motion. Now, if you run this trajectory through, just like with the every chapter in every electrodynamics book, intro electrodynamics books, Jackson and Zangwell, talks about moving point charge. It's been a staple for our understanding of radiation, especially with respect to synchrotron or Bremsstrahlung radiation. And you just turn the crank and compute the power distribution or the power. You can do this completely analytically, and you get some pretty simple results. Here you can see that when the electron's speed of beta is zero, that prefactor out in front causes the power to be zero. When the speed reaches s, the post factor here turns also into zero. So the power is zero in the far past and far future. So there's this time period where you have an emission of a lot of power, but then asymptotically you have no power. So turn the crank, solve for the spectrum using spectral analysis. This I omega represents the spectrum. It's the amount of energy radiated per color of the photons, and you can get a spectral distribution. And immediately one sees a very interesting characteristic on the right-hand side. You can see this Planck factor. This is a well-known Planck distribution that characterizes Bose-Einstein statistics of the photons. So we can integrate this over the solid angle, and the Planck distribution remains robust, and you get a spectrum, an analytic spectrum. It depends on the electric charge, E squared. It also depends upon this factor in parentheses, which depends on the final speed of the electron. So this is a one-dimensional Planck distribution from an accelerated electron. Now, one-dimensional meaning that it's not the Planck distribution that we see from the sun or from the universe or from your oven, but in fact, it is one-dimensional Planck spectrum, which does have some corresponding phenomena in the real world, namely, a resistor. It's been well known since 1928 that if you just have a wire in a normal room temperature room, that you'll have a current moving through it. And that current is white noise. It's called Johnson-Nyquist noise. And the electrons have a temperature. And it's a one-dimensional Planck distribution. So this is a real-life thing. It's not to be looked on as some sort of artifact or anything. The one-dimensional Planck spectrum has been measured inside a circuit. So I can also say that the black hole is a one-dimensional Planck spectrum. So black holes radiate with 1D Planck distribution. So what's interesting is that if you take this, the color to be very, very red, super long wavelengths, and very, very small frequencies, this infrared regime, you get a constant. And it turns out this is the spectra for infrared spectra for all scattering events. And so there's a bit of universality in this result, at least in the infrared regime. And so you may also recognize that this is actually the spectra for the photons emitted by an electron during its creation from a neutron. So when a neutron converts into a proton and an electron, the electron goes accelerating away and gives off some light, some gamma rays. And that light has, to lowest order, this spectrum, a constant spectrum that's independent of frequency. And so we, me and my colleagues, decided to look at beta decay, where a neutron is converted into this electron, and check out to see if our spectrum, I omega, could characterize the color of light from beta decay. And it turns out, just very briefly and in a nutshell, this is the only slide I have on this, but I hope very, very much that our paper will come out very soon, maybe within a week or two, where we have taken our spectrum, this I omega, that's this one-dimensional Planck spectrum, and we simply plot it with the particles versus the color. And when we plot it, and then we also plot the data from free neutron beta decay using the RDK II experimental data that was published in Nature and Physical Review Letters, we find very good agreement to statistical agreement. I believe the result is at least as good as a 3 sigma result. And we don't have to do any fitting of our spectrum to the data. In fact, we just simply plot our spectrum and the data agrees with it to uncertainties. So we have experimental confirmation that the radiation from an accelerated electron is indeed thermal and follows a Planck distribution, a one-dimensional Planck distribution. If you take that spectrum and you integrate over all the colors, you get the total energy, which happens to be the total energy radiated during beta decay. So everything is quite consistent. This is a classical picture here, right? I mean, beta decay is a quantum field theory result. It's a weak nuclear process, and we're using standard classical electrodynamics to describe the thermal emission that happens during beta decay. It's very impressive that classical theory could be so powerful here. But this, of course, is the lowest order contribution to the energy. There are higher order corrections, but those higher order corrections in most circumstances are extremely small, and they are negligible for our purposes. But to give you an idea, I believe this amount of energy, at least in some contexts, is 99.7% of all the energy radiated. So we can be pretty accurate with classical theory, at least to lowest order. So now that I've hopefully maybe stimulated or given you some interest in this spectral behavior for the electron, I'd like to motivate the trajectory itself through a very interesting mapping, a duality between the electron and the flying mirror. It turns out that if you have a flying mirror that moves along the same trajectory, you get the same energy, effectively the same energy. They only differ by a constant. In the mirror's case, you have h bar, and in the electron's case, you have the electric charge squared. So there's a deep connection between the flying mirror model, which is a 1+1 dimensional toy model, very low dimensions, very artificial, you might naively assume. And whereas the electron is an ordinary electron in 3+1. So, but it turns out that this mapping between the electron and the mirror, it works for all trajectories, at least asymptotically inertial ones. And Lamar power has an analog where the power is proportional to the acceleration squared. And the only difference here is by a constant, where h bar is effectively turned into the electric charge. It works for the Lorentz-Abraham-Dirac force, which is simply the jerk. It's a time derivative of the acceleration with respect to the proper time. It's in fact quite an incredible functional identity between the moving mirror and the electron. Now, this has been known for some time, at least to some extent, worked on by a 96-year-old man now, Vladimir Ritas, which we are in contact with, and he's has been very committed to understanding this duality for the last 30 years, publishing paper after paper, and it, in my opinion, has not gotten the attention that it deserves. But you can see that there are several quantities that have a very easy to understand analog between the two. Not only the force, power, and energy, but the amount of particles as well. And the object that we're interested in is the temperature. So if you use Stoney units, say where a connection between temperature and frequency is understood with the scale of E squared, you get an analogous object for temperature. If you use our familiar Kelvin, it turns out the temperature of the electron is actually equal to the temperature of the mirror. So the constant here is in joules per second. It's this E squared versus H bar, and the difference between these two models is exactly 10.9, a factor of 1 over the 4 pi times the fine structure constant. So here's the difference between the Stoney scale and the Kelvin scale. So it really doesn't matter what constants you use, but what it does tell you is that to use Kelvin, regardless of whether you're using quantum ideas or not, H bar will make an appearance. So the H bar could be very misleading whenever you see it, because anytime you're dealing with temperature, the Kelvin is defined by H bar. You've got to use H bar if you want to use Kelvin. So it doesn't mean that it's a quantum effect. And if we use Kelvin, then we would also get the same formula as Hawking evaporation, flying mirror, and the Unruh effect with this H bar out in front. So that being said, I'd like to maybe say a statement of speculation where it could be that it might be possible through the equivalence principle, because gravity hasn't been quantized and the way we understand general relativity is completely classical. It could be that Hawking evaporation could be understood from a purely classical point of view. And using this model, we might be able to make some headway on this type of idea, so this type of direction here. So it could be that Hawking evaporation is a classical acceleration temperature effect. But nevertheless, that's speculation. So this model is classical, and I'd like to end this talk with just one statement on the dynamics of what kappa means. So if you take the object called the peel, or the local acceleration, or the effective temperature function, which is just the second derivative of the advanced time over the first derivative, you'll get an object that in a double limit of fast electrons' final speeds and late times, this peel equals the kappa. So this is it's not that nice, it's not that intuitive, and it's not that pleasing, but it is a connection between dynamics and the scale of the system. So you can see that, when you plot this peel, you get a nice plateau where the plateau is equal to kappa here in normalized units. So there is a connection between kappa and the dynamics of the electron. So in conclusion, I want to just say, if you're going to walk away from anything from this talk, I'd like to tell you that the thermal spectrum from an electron, it's one-dimensional. That's pretty interesting, just like a resistor, just like a black hole. And number two, there's a holographic duality between an electron and a mirror. So the mirror is in 1 + 1 dimensions, the electron's in 3 + 1. This is really neat. All the information of the mirror system can tell you everything you want to know about the electron system. So this is like a holography. And then the radiation from an accelerated electron has this temperature. So with that, I'll take back my time, and I very much appreciate your attention.
Thank you so much, Mike. Nice. So are there any questions from our Zoom audience? Yes, Morgan already has his hand raised. So please, Morgan, go ahead.
So one of the things that I really liked about this analysis is that it comes out as a one-dimensional Planck distribution, and that has some grounding in the kind of older literature in terms of this resistor. And so I was curious if you know, the fact that you're getting this one-dimensional noise, a Planck distribution noise in these resistors, is there in some way that just by chance that all these resistors that we've been making have some sort of analog horizon and some infrared in there, or is there anything that you can anticipate that would be some sort of an analog of a horizon that's creating this this one-dimensional distribution, but in resistors?
That's really good. That's a good question. So to think of the idea of a horizon in terms of the resistor, I haven't thought about it because, you know, I can't think of anything that comes off my head of how a resistor could have this horizon. But I have thought a little bit about the fact that they're both systems involving electrons, which is curious. And there also are both systems that appear to be important in the infrared. So the structure, the fact that the electron has no structure, the fact that all scattering processes in the infrared give the same spectrum, this suggests a type of universality. And I bet you there's clearly a link between the two systems in the infrared, and maybe by the fact that they're electrons. But as far as a horizon goes, that would be an interesting thing to investigate. So there's not a strict horizon in this electron, at least from the idea that there are light rays that never hit that never reflect off of the electron or never hit the mirror. So it's not like it's not like the black hole horizon or a trajectory that goes to light speed. This actually is always time-like. So there actually is no horizon. So that's good that you remind me. So in fact, I bet you that it doesn't have to do with a strict horizon.
Okay. It's interesting. Very cool stuff.
Yeah. Thanks for the question.
Thank you so much, Morgan. Thanks, Mike. So let's thank Mike again.